Previously, we discussed the principles of filling electrons into atomic orbitals. We looked at the Pauli's exclusion principle, we talked about the of Bohr's principle, and we discussed the Hund's rule of maximum multiplicity. Under Hund's rule of maximum multiplicity, the key point derived from there is that in filling degenerate orbitals, these orbitals are filled with single electrons first before you can start what? Pairing. One of the reasons we gave for filling these degenerate orbitals with single electrons before pairing was to reduce the electrostatic force of what? Repulsion. Okay, electrons are charges, and the study of physics helps us to understand that charges can also generate magnetic field. It therefore becomes important for us to look at the concept of magnetic moment. Alright, so that's what we have on the board here. We're going to discuss. Magnetic moment is that force of repulsion or attraction that an element experiences as a result of unpaired electrons. So it is expected that once there are unpaired electrons in an atom, that element will experience force of repulsion and force of what? Attraction. This is the concept of magnetic moment. The unit of magnetic moment is Bohr magnetum. Bm, alright? And this magnetic moment, which we're using this symbol mu for, right, is equal to square root of n, open bracket, 2 times n plus 1, close your bracket, where in this case n is the number of unpaired electrons in this atom. What can be used to measure the magnetic moment? We have this instrument called the Gauge balance. So the Gauge balance is used to measure magnetic moment. Now let us look at this formula called the spins only formula that can be used to estimate n, that can be used to determine the value of n, that is the unpaired electrons. Of course, looking at this formula, it's very clear that somehow magnetic moment is dependent on the number of what? Unpaired electrons n. So if we assume, I'll say that okay, magnetic moment is entirely obtained from the unpaired electrons, that is the unpaired electron spin. It therefore means that we can use the spins only formula to determine or estimate the value of n. Once we are able to determine the value of this n, that is the unpaired electrons, then it's possible for us to work out the shape of the complex of the oxidation state of metal and octahedral complexes. We can do that by using valence bond theory or crystal field theory. In the next video, we're going to see classification of complexes into 2 of them, and possibly some examples of complexes that fall under either of these 2 classifications. Let us now consider classification of complex compounds, alright? Complexes are generally classified into 2. One of them is diamagnetic complexes, and then the other is paramagnetic complexes. And these complexes are identified based on the behavior when they're exposed to a magnetic field. 2 things happen, right? So let us talk about diamagnetic complexes. For diamagnetic complexes, they tend to move away, to move out of a magnetic field. When they are placed between the poles of an electromagnetic field, something happens to their weight. For diamagnetic complexes, they weigh less. As their weight reduces. Is that okay? When placed between the poles of an electromagnetic and the electromagnetic field is put on, their weight will reduce. So you want to take note of these 2 points. One of it is that for diamagnetic complexes, they move out of the magnetic field. And of course, their weight, is that okay, reduces when they're found between the poles of an electromagnetic field. An example of diamagnetic complexes, we have more of cobalt 3 complexes. More of cobalt 3 complexes. Although some cobalt 3 complexes are paramagnetic, but most of them, they fall under diamagnetic. An example of them that is a diamagnetic complex is this. This is tetraaquadiamine cobalt 3 chloride. Alright, this is a diamagnetic complex. Now let us look at paramagnetic complexes. For these complexes, they tend to move into a magnetic field. And when you place them between the poles of an electromagnetic field and you put on this electromagnetic field, the weight of paramagnetic complexes will increase. Okay, it becomes more. So take note of this, that they tend to move into magnetic field. And then talking about their weight, they weigh more. The weight increases when placed between the poles of an electromagnetic field. As an example of a paramagnetic complex, we have this, about 3 hexa remain still. It's an example of paramagnetic complex. Please, I urge you to check on Google. You can browse that to see other list of diamagnetic complexes and paramagnetic complexes, alright? You could see others of the manganese, those of copper, those of nickel, alright, iron, and many more. Please take note, paramagnetism is principally due to the presence of unpaired electrons. So having considered the quantum numbers, the principles of arranging electrons into atomic orbitals, of course the magnetic moment of an atom, we now want to apply all this knowledge that we've got already to solve this problem here on the board. Alright, so please come along with me, let us do this together. The question here reads, the last shell of a given element is 4d8. Fine, we've got 8 things here to find. There's 8 questions under this, is that okay? The first, we have to find N, L, M, and S. That is the principal quantum number, the azimuthal quantum number, the magnetic quantum number, and the spin quantum number values. How many electrons are in the outermost shell? How many electrons are in the penultimate shell? How many electrons are in the antepenultimate shell? How many unpaired electrons are present? How many paired electrons are present? What is the magnetic moment? And then the last part of the question, what is the atomic number of the atom? So let us take this one after the other. First of all, I want to take note that the last shell of the given element is 4d8. So I would write last shell. Last shell is given as 4d8. This simply tells us that the last electron enters the 4d orbital. Is that okay? The 4d orbital. That's where you have a last electron. Okay, now, on the basis of that, let's now move on. The first part of the question, we have to calculate the quantum numbers. We'll start with N. N is equal to... Now, let's quickly take our mind back to Bohr's principle, the building block principle. You take note that we combine the principal quantum number N with azimuthal quantum number L to generate that 1s, 2s, 2p, 3s, 3p, 4s, 3d, After 3d, you now have 4p in that order. Now, the numbers attached to these alphabet S, P, D, F, the numbers attached to them are the principal quantum numbers N. Does that make sense? So in this case, what number is attached to D here? The number attached there is 4. You can see that. So the principal quantum number is equal to 4. Does that make sense? So that's the first solution here for the principal quantum number. Okay, now let us look at the second part. The second part, we are to determine the value of L, the azimuthal quantum number. To get L, we want to recall that L is equal to N minus 1, principal quantum number minus 1. Alright, that helps to give the final value of L. So this is going to be 4 minus 1, which will give us 3. So the final value of L is equal to 3. You know that the value of L ranges from 0 increasing. Is that okay? So 0, 1, 2, 3. Those are the values we have for L in this problem we are solving. So I'm going to say that it implies that L is equal to 0, 1, 2, 3. But hey, we are not done yet. We are not done. Out of these 3 values, or 4 values here, okay, because these 0, 1, 2, 3 represent subshells, azimuthal quantum number, L equal to 0 is the S subshell, L equal to 1 is the P subshell, L equal to 2 is the D subshell, and then L equal to 3 is the F subshell. So out of these 4 values, which one actually is the value of L for this element? Is that okay? Now take note that the electron entered the 4d orbital lastly. Is that okay? The 4d orbital. And so D corresponds to what? To 2. Let me make a statement in that here. Since D subshell corresponds, all right, to L equal to 2. What's the implication? Therefore, we can simply say that the value of L is equal to 2 in this case. Are you following? Because the last electron entered the orbital. D corresponds to the subshell 2 as middle quantum number 2. So it simply means that L is equal to 2. Even if we have 0, 1, 2, 3 values, the actual value of L is equal to 2. Alright, answer. Now we're going to look at the magnetic the magnetic quantum number n. To get the magnetic quantum number, remember the value ranges from minus L through 0 to plus L. So it implies that the L value actually obtained here is 2 for this analysis. So n will now be equal to minus 2, minus 1, 0, 1, and 2, telling us that we have 5 orbitals. And of course that is true. D subshell contains 5 degenerate orbitals. So recall that we made all this analysis when we were trading this topic. Is that okay? And that actually is agreeing with what we're obtaining here. Alright, now we've obtained the value of this. So this is the answer for n. The answer for n. We shall now go for the spin quantum number. For us to obtain the spin quantum number, we are going to draw the orbital of this last shell. Is that okay? The orbital of the last shell is given as this. Remember, D has 5 degenerate orbitals. So 1, 2, 3, 4, and 5. How many electrons do we have there? We've got 8 electrons there. So we're going to distribute the 8 electrons. 1, 2, 3, 4, 5. Remember, if you are filling degenerate orbital, this is the 4d8s, supposedly. If you are filling degenerate orbitals, you fill singly first, according to Hund's rule of maximum multiplicity. So we've got 5 electrons filled into the 4d orbital, remaining how many? 3. So we'll come back and start pairing. So have 1, 2, because this is 7 already, and then 8. Did you take note that the last electron faced downward? The spinning is a downward spin, that is anti-clockwise spin, right? And that corresponds to spin quantum number equal to minus 1/2. So we're now going to say that it implies that the spin quantum number is equal to minus 1/2, that is 1 over 2. It's an anti-clockwise spin or downward spin. Answer. Please, the basis is on the fact that the last electron spins downward. This is where we located. The quantum numbers, let me start them so that you take note of where we actually started calculating the values of the quantum numbers from. Alright, that's good. Now let us look at the number of electrons in the outermost shell of these elements. This last shell is giving us 48. Okay, so that's the second part of the question. For us to deal with the number of electrons in the outermost shell, take note, the outermost shell is also known as the valence shell or the ultimate shell. Is that okay? So this would require that we write out the electronic configuration of this element. The name of the element was not specified, but we know that the last shell as given from the question is 4d8. So we're going to write our electronic configuration down to 4d8. So electronic configuration. So we go, this is going to be 1s2, let me use black marker, 1s2, blue marker rather. Okay, then 2s2, 2p6, 3s2, 3p6, 4s2. After 4s, you move on to 3d, 3d10. Remember, when you get to 3d, the next move will be dps, dps. Is that okay? So 3d10, the next will be p, and p will be 4p because we've got 3d here, 4p6. Then the next will be 5s2. After 5s2, another dps is to repeat. And then that D will be 4D, of course, it has brought us to this, so that will be 4D8. Okay, now this electronic configuration is for which element, which atom? Let's find out. Okay, from this 1s to 2p6, we've got 10 electrons. Then 3s to 4s, we've got another 10 electrons, giving us 20. This 3D, 10, giving us 30 electrons. This will be 36, all right? This will be 38, then this will be 46. So this element is palladium. This element is palladium. This is palladium. This is palladium. Okay. Now there is something unusual about palladium I need you to know, but I will not go too deep into it because at this level the concept might not be quite very clear. But I'm going to quickly use the idea of Bohr and Medullum to bring the analysis a bit clear. Is that okay? Remember, according to Bohr, electrons are being filled into the orbitals of lower energy, and then you start increasing them. Is that understood? Please look at this. Do you notice that we filled 5s2 first before 4d8? Is that okay? Which likely tells us that this d orbital has higher, that is 4d has higher energy compared to what 5s2. Okay, the 5s2 electrons will be transferred to 4d10. So let me transfer it this way. I'm going to promote it, which means that coming over here, it means that these 5s2 electrons no longer exist. The reason is this. Look at this is 5, principal quantum number 5. S subshell, you remember that the azimuthal quantum number L is equal to 0. 5 plus 0 will give you 5. This is in accordance with Medulong N plus L rule. N plus L. N plus L rule. Is that okay? Where L is azimuthal quantum number and N is the principal quantum number. So this principal quantum number here is 5. The azimuthal quantum number L for this S subshell is 0, you know. 5 plus 0 will give us 5. Then come to this D. This is 4D8. Now what we have there, the D value, you know, azimuthal quantum number there is 2. Then the principal quantum number is what? 4. 4 plus 2 will give us 6. Which means that, okay, maybe this is at higher energy level 6, you know, compared to that of 5. Does that make sense? And then again, this 4D is unfilled. It's not completely filled, rather. It's not completely filled. And for palladium, it's more stable when the D orbital is filled completely first. So that's part of the reason why we have to promote this to the 4D8 to make it 4D10. But anyway, this is an unusual concept that applies to palladium. You want to take note of that. We hope that in subsequent videos we are going to explicate this concept more clearly. Alright, so this would not mean that the outermost shell or electron would now be obtained from the 4 principal quantum numbers, that is principal quantum number 4, because this 5s2 is transferring to this 4d completely, you know, nothing will be here again. And even from the point you see, the last shell is giving us 4, the principal quantum number 4, 4d8. So we take note of this, and then we'll take note of this. So that's going to be 4s2, and then 4p6, and 4d10. Take note, we transfer the 2 electrons to this. Therefore, they will be equal to 2 plus 6, 8 plus 10, 18. 18 electrons in the outermost shell. There are some cases you would see, perhaps, let's say you browse and find out the number of electrons in the outermost shell of palladium, you would see like 10. It's not really wrong. That is when we consider only this 4d8. But there's something I want to know. I've used the expanded shell configuration because when dealing with maybe the number of electrons in the outermost shell, penultimate shell, and antepenultimate, we expand it. We consider the same principal quantum numbers. That's the principle. Is that okay? That's the guy. Which means that in this case, since I have other 4 principal quantum number 4s, I'm going to combine them together, calculate the total number of electrons there. Is that okay? So I have 4d8, 4p6, and 4s2. Those that mention that the electron in the outermost shell is only 10 is based on the fact that they consider that, okay, we are taking just the 4d. Is that okay? That's just very different. But in essence, dealing with the expanded shell, which is actually what is required of us here to do, is that okay? Because when you come to a particular principal quantum number, for example, principal quantum number 4 has the S subshell in it, the P subshell in it, and then the D subshell. All of them 4S, 4P, 4D. Does that make sense? So you have to put them together, add the electrons to get the total number of electrons in that shell. As we move on to the third part of the question, how many electrons are in the penultimate shell? So we want to get the number of electrons in the penultimate shell of these elements we are dealing with, okay? So penultimate shell, simply the shell inner to the outermost shell, or the shell before the outermost shell, depending on whether you are entering into the atom towards the nucleus or moving outward, you know, away from the nucleus. Okay, so if we say you are moving away from the nucleus, okay, let's have something like this. So if this is my nucleus, have this, then we'll have this. Alright, so we refer to the inner one, this as the antepenultimate. Permit me to use AP for it, antepenultimate shell. Okay, and then we refer to this one as the penultimate shell. Permit me to use PS for it. And then the one outside, refer to it as the outermost shell. Outermost shell, or you can call it the valence shell, or you can call it the ultimate shell. So take note of that. Now, how do we get the number of electrons in the penultimate shell of this element? The penultimate shell would then be the element, or the shells rather, with principal quantum number 3. So I'm going to take note of them. This is one of them. Okay, this time around, let me Okay, we have this. Let me underline this one and this one. I had wanted to star before, but let me just underline. Or let me underline and star. Okay. All right. So these are the penultimate shells. So we're gonna have 3s2. We're gonna have 3p6, and then we'll have 3d10. 3d10. And this is going to give us 18 electrons. 18 electrons in the penultimate shell of this element. Okay, now let us look at the fourth part of the question. Number of electrons in the antepenultimate shell. Penultimate shell. Once again, this would be the shell that is inner to the penultimate. And that's going to be those with principal quantum number 2. And that's going to give me this and this. So these are the antepenultimate shells. There, I'm going to write 2s2 and then 2p6. And you notice that there are 8 electrons in the antepenultimate shell of this palladium. Let's now look at the fifth part of the question. How many unpaired electrons are present? Considering this 48 directly, we could see that there are 2 unpaired electrons. The d orbital is meant to take 10 electrons fully, is that not so? So given the normal electronic configuration of palladium, on the condition that this 4d is 8, it means that there are 2 electrons left to complete it. Is that okay? Which was the reason why we did a transfer, earlier from the 5s2 shell to the 4d8 to make it 4d10. But of course, to do that, let's just quickly draw this out, okay? We're going to draw this out. The d subshell. It has how many degenerate orbitals? 5 of them. Okay, so 1, 2, 3, 4, 5. This first degenerate is dxy. The second one is dyz. The third one is dzx. The fourth one is dx squared minus y squared. Then the fifth one is dz squared. So this is how the d degenerate orbitals are presented, just like you have px, py, and pz. Is that okay? Now, let us fill up the degenerate orbitals here with the electrons and see what we're going to get. Alright, all these are 4d, 4d8. So we're going to have 1 electron, 1. So we fill singly according to Hund's law of maximum multiplicity. We've got 5 electrons here, so we can start pairing. This is 7, and this is what? 8. Alright, so you notice that there are 2 unpaired electrons there. So that is that for the fifth part of the question. Then, how many paired electrons are present? How many paired electrons are present? How do we get the number of paired electrons that are present? Of course, I'd like you to take your mind back to the question number, question number 3. Remember, question number 2. We wrote out the electronic configuration of this atom. And how many electrons we have totally for this atom is 46. So for us to get the number of paired electrons will be equal to the total number of electrons is 46. So let me write out a formula that will guide us. Total number of electrons minus unpaired electrons, then divided by 2. The division by 2 is for us to get the number of pairs. Remember, a pair is made up of 2 electrons, so that's the essence of this divided by 2. So we're going to do the total number of electrons in this atom. We will subtract those that are unpaired, and we have 2 which are unpaired. If you subtract the 2 from the total number of electrons, what you're going to get will be total number of electrons in the atom that we actually paired. Now, how do we get the paired number? We divide it by 2 because each pair contains 2 electrons. Now, this is equal to 46. We found out that this is atomic number 46, so it has 46 electrons. Then minus how many unpaired electrons? 2, and then we'll divide this by 2. So this will give us 44 divided by 2, and this will be equal to 22 paired electrons. This is the number of electrons that were paired in this atom. Alright? 22 paired electrons. Now, we want to look at the last part of this question number 7 and 8 of this question we're analyzing here. The seventh part of the question, we are asked to obtain the magnetic moment. Magnetic moment. We use this symbol for the magnetic moment. Of course, you would recall that we established a formula to be square root n open bracket 2n plus 1, where n is the number of unpaired electrons. Unpaired electrons. Now, how many unpaired electrons do we have in this case? In this, our analysis, we established already from alright, that's the fifth part of this question, that n is equal to 2 electrons, the number of unpaired electrons. So it means that the magnetic moment will be square root of 2 brackets 2n, which is 2 times 2, right, 2 bracket 2n, which is 2 times 2 plus 1. Working out this, you're going to get 2 bracket 5, which will give us square root of 10. Square root of 10, if you obtain it, is equal to 3.16. 3.16. Remember, the unit of magnetic moment is Bohr magnetism. Bohr magnetism. So this is the result of the magnetic moment. Of course, the last part of the question, which is question number 8. Question 8. We are asked to obtain the atomic number of this. So atomic number is equal to 46. Is that okay? So we're done with this. In the next video, we're going to introduce latest rule that's used to calculate screening constants. And of course, to do that, we'd like to discuss the concepts of actual nuclear charge and effective nuclear charge due to the shielding of inner electrons and due to the electrostatic pull of the nucleus and the electrons that orbit it.